Maybe you could say more about what makes understanding the neurological source of dreaming at all relevant to understanding consciousness and what we've just been talking about. I told you the cat would be making her appearance.
Some of my best friends are cats. Don't worry about that. I said some minutes ago that I was interested in dreams because they are conscious states that occur in the midst of sleep. I mean, it's truly fascinating that while we're unconscious, which is a sort of definitional almost of sleep, is that you're unconscious. That this unconsciousness is punctuated by these intensely conscious experiences. So when I sought the brain mechanisms of dreaming, let me say, first of all, at that time, I began my research on that subject in the mid-1980s. And at that time, the standard view was that the brain mechanisms of dreaming were identical with the brain mechanisms of REM sleep. REM sleep is generated, just to put it very simply, by mesopontine tegmentum cells, part of the reticular activating system, which are cholinergic. So the neurotransmitter, or rather I should say the neuromodulator that is sourced there is acetylcholine, which activates the forebrain. And according to the standard model of that time, which was Alan Hobson's model, it activates the forebrain sort of chaotically and randomly, because this is very widespread activation from the mesopontine tegmentum. And the cortex, to quote Hobson, makes the best of a bad job. It's got all of these sort of images, perceptual images of various modalities and thoughts and feelings and whatnot, and intentions are all activated. The cortex being the organ of the mind, that if you activate it, you're going to organize, you're going to activate mental contents. And his view was that these are then just joined together. That there's that's the synthesis. He speaks of activation synthesis. He said the cortex's job is to synthesize these randomly activated cortical elements. And he made the point that the dream, it is so nonsensical, so unrealistic, so utterly like our ordinary experience, precisely because it's randomly generated. There's no intrinsic meaning. It's not really referring to anything going on in the outside world. This is endogenous activation from the brainstem. And so it creates this chaotic splodge. And he says that the dream is therefore like an ink blot. There's no meaning in it. It's not psychologically motivated. You can come to that ink blot after the fact and you can find meaning in it. In other words, you can project meaning into the ink blot, but the ink blot itself is mindless, meaningless, without intentionality. And he also emphasized the fact that acetylcholine is, to use his phrase, motivationally neutral. So my studies, which differed from his in that I didn't study rats, but rather human beings. The main subjects of REM sleep research had been rats and cats, which is for all sorts of good reasons that they focused on these animals. But the downside of studying them is they can't speak, and therefore you can't monitor the subjective side of. It takes us back to the very starting point of our discussion. You leave out the subjective observational perspective. So that's why I studied human beings. I wanted to know how are the contents of dreams altered by damage to different parts of the brain. And that led me to the absolutely surprising discovery that patients who lost the capacity to generate REM sleep nevertheless retained the capacity to dream. So you can dream without having any REM sleep. And what is more, I found that there were other patients who lost the capacity to dream in whom there was a preservation of REM sleep. So these are not the same thing. REM sleep and dreaming are what we call doubly dissociable functions. So my interest then turned to the brain mechanisms that generate dreams as opposed to the brain mechanisms that generate REM sleep. And the main mechanism there turns out to be something called the mesocortical mesolimbic dopamine circuit, which is sourced in the reticular activating system in an area called the ventral tegmental area, and rises up from there into subcortical motivational structures and beyond. Now, I told you what it's called, but another functional name for this system is the brain reward system. I mean, this is anything but motivationally neutral. It is intensely motivating, positively motivating system. Hence the name brain reward system. It's also been called all sorts of other things: seeking system, wanting system, curiosity, interest, expectancy system, and so on. So my search for the brain mechanisms of dreaming brought me to this system, which was, as I've already told you, what made me realize perhaps Freud was onto something when he said dreams were motivated mental states, but also to another fact, which is that the reticular activating system, although it has an arousal function, as we've known since 1949, this arousal generated by the reticular activating system is not motivationally neutral. It's not just blank wakefulness. It is intensely affective. This circuit is just one example, the one that turns out to be the driving force behind a dream generation. But the same applies to many other reticular activating circuits. So, for example, so the one I'm talking about is modulates dopamine, but the one that modulates serotonin, which plays such a pivotal role in the treatment of depression, it's also sourced in the reticular activating system. Likewise, norepinephrine, which plays, so norepinephrine, psychiatrists fiddle with it to treat anxiety. They fiddle with serotonin to treat depression. They fiddle with dopamine to treat psychosis. These are not the sorts of things that anesthetists are interested in. These are the sorts of things psychiatrists are interested in because they have to do with feeling, with emotion, with affect. So my dream research led me to the brainstem, because this system is sourced in the brainstem, but it also led me to the realization that the arousal that emanates from the brainstem is not neutral. It's not just quantity of wakefulness. It's not just a level of consciousness. It has content and it has quality, and that content and quality is affective. So we'd known since 1949 that all consciousness is contingent upon brainstem arousal. But what these findings, and it wasn't just my dream study led me to a body of literature which was then beginning to develop independently of my efforts, led by somebody who ended up becoming my closest colleague in consequence of this, named Jaak Panksepp, that he was demonstrating that all basic affective states, raw feeling states, are generated from upper brainstem mechanisms. So that's where dreaming fits in, and brings us back to the topic of the hidden spring. I said to you earlier that I thought we were looking in the wrong place, that we, if you want to understand the mechanism of consciousness, you shouldn't look to the cortex antivision, because the mechanism of cortical vision is not intrinsically conscious, but the mechanism of brainstem arousal is intrinsically conscious, and what is more, it produces a particular quality of consciousness or range of qualities that we call affect. And so I came to the view that if we want to understand consciousness, we need to understand its most basic form, namely affect, and that this is the right place to start, not only because it's its most basic form, but also because if you understand the mechanism of feeling, then you have to explain why it feels like something. Unlike vision, you can understand the mechanism of vision without knowing why it has to feel like something to see. But you can't explain the mechanism of feeling without explaining why it has to be felt. If Mary were an affective neuroscientist, and she understood all the mechanisms of how a feeling is generated in the brain, she would have to explain those mechanisms, would have to explain why they feel like something. That's the whole point of those mechanisms. So that's sort of that takes us to pretty much the heart of the argument of what the hidden spring is about.
As an aside, I mean, there's often a questions raised. How can you tell if some sort of organism is capable of consciousness? Now, we're able, as far as I can tell, to tell if a creature is dreaming by examining whatever's going on in their brain. Is it the case that anything with the reticular activating system in the upper brainstem is capable of dreaming?
Well, the problem is unfortunately more complex than the way you've just framed it. I'm happy to agree with you, but many people would not be happy to agree with you, because they would say, just because you can see that the upper brainstem is activated during sleep, and that you can see that it is activating the cortex, and you can even see, as we have been able to in recent years using some of the wonderful techniques and methods that we now have at our disposal, you can even show that there are things that were learnt during the day. You see the same pattern in the hippocampus that night during dreaming sleep as you saw being acquired during the dream day. You can see also the patterns in visual cortex that coincide with the images that human beings report they had seen during the dream. So there's all sorts of good reasons to believe that this sort of neurophysiological evidence of dreaming is indeed just that, evidence of dreaming. Nevertheless, many people will say, well, that's not a dream. That's just activation of certain parts of the brain. You can't be sure that there's actually a dream attached to that. But if we detach ourselves from that problem of other minds, is basically what that is. That you have to be the dreamer to know whether they're dreaming. If we detach ourselves from that philosophical conundrum and just look at it purely scientifically, then yes, indeed, all the evidence suggests that all mammals dream. All mammals, all of the architecture in the human brain that we know is responsible for dreaming, all of the physiological processes that we know coincide with dreaming, all of those things happen in all mammal species. So there's very good reason to believe that all mammals dream.
But then there are other animals with brain stems, like fish or amphibians or birds. Do we also have reason to think that they dream? And what I'm getting at is, if the same source of dreaming is the source of consciousness, we might have at least good prima facie reasons for classifying. Okay, these are the conscious animals. These are nematodes. We don't count them. They don't have a brainstem.
Yeah, I want to draw a distinction here between dreaming consciousness and raw feeling. Dreams are suffused with feeling, but they also include complex perceptual experiences, which are not just feeling. They are things that we see and hear and think, etc. That's something in addition to the raw feeling. These properties of dreams must be contributed by the cortex. The cortex is where it's the activation by the brainstem of these cortical structures which enable us, if you don't mind me putting it this way, to feel our way into those cognitions. So the cortex is producing these complex representational gymnastics, and the upper brainstem modulates them, and in this way we render them conscious. So if we separate those two bits, I would say all mammals, there's every reason to believe that they dream because they have both upper brainstem structures of the kind I'm talking about, and they have cortex. When it comes to birds and several other vertebrate species, they have a pallium. They have a homologue of cortex, but many non-vertebrates have no. I mean, many vertebrates, non-mammalian vertebrates, don't have any cortex to speak of. So I would say that all vertebrates have raw feeling, but I wouldn't claim they all have dreams. I would say they all have raw feeling. And again, I have to say, every prediction arising from that hypothesis is confirmed. Like, for example, you stimulate the structures which generate pleasurable feelings, the brainstem structures which generate pleasurable feelings in humans. You predict, if I were to stimulate this structure in a fish, it is going to seek to repeat that stimulus. So if you give them a little lever that they can prod with their snouts, you predict they will keep prodding that lever that switches on the electrode because it feels good. And that's what they do. And conversely, with aversive stimuli, which are generated in parts of the brainstem which produce unpleasant affect, they avoid those levers. So I'm just giving you one silly little example. In fact, let me give you a better example. Zebrafish, or zebrafish, as you guys say, they have the same brainstem architecture, being vertebrates, and you put them in a tank, and you put all the food on this side of the tank. They tend to congregate there. That's called conditioned place preference behavior. They prefer to be there because that's where the food is. Now, on the other side of the tank, you introduce cocaine. Cocaine is not good for you. It's not nutritional, but it feels very nice to imbibe cocaine. So a prediction arising from the hypothesis that zebrafish have feelings, a prediction is that they will start to congregate where the cocaine is. And that's called hedonic place preference behavior. They're conditioned only by a feeling, not by anything that's nutritionally good for them. And that's exactly what they do. The fish head for the cocaine. And the same applies to morphine, and the same applies to amphetamine, and the same applies even to nicotine. Zebrafish like those substances. So, this is the sort of evidence I'm referring to when I say that all of the predictions arising from the hypothesis that all vertebrates have raw feelings, every time we ask that question, the answer we get is yes.